Thank you.
Yeah, thanks. Hello everyone. So my name is Yue Song. So I'm currently with the Department of Electrical and Electronic Engineering, the University of Hong Kong. So today I'm very glad to give a talk on the network-based stability analysis of electric power systems. And in this talk, I will survey some of our recent results on power system stability analysis that takes a network-based perspective, which is different from the traditional methods. So these works are done in collaboration with Professor David Hill and Dr. Tao Liu, who are also with the same university. So my talk consists of the following 4 parts. So first, I will briefly introduce the motivation of network-based research. Then we will see some representative network-based results on so-called rotor angle stability, which is an important class of stability problems in power systems. And further, I will quickly go through some other results relating to other types of stability issues in power systems. And finally, I will finish the talk with a summary. So let's begin with the motivation. So let's have some basic knowledge for power systems and power system stability before proceeding further. Electric power systems are a critical part of the infrastructure where the users get electricity supply from the generators or power plants via power transfer over the underlying power network. The power system stability refers to the ability of a power system to regain a state of operating equilibrium point after a disturbance. So to guarantee stability is a basic requirement for power system daily operation. According to the main system variables in which the instability phenomenon is observed, power system stability can be further classified into rotor angle stability, voltage stability, and frequency stability. And in this talk, we will mainly focus on the rotor angle stability in the small disturbance case, which means we can apply the linearization method to the original nonlinear model of power systems. And we will also talk a little bit about the voltage stability. So let's move on. There are 3 main components in a power system. Say the generators, which is the power sources, the loads, which is power consumers, and the power network. So the generators and loads refer to the nodes in the system, which are interconnected via the power network structure. And the system model for stability analysis generally takes the following form here, where the function Fi refers to the local dynamics of the nodes, and the parameter Aij reflects the power network structure. It is non-zero if node I and node j are connected. And the function Gij describes the interaction between the 2 nodes. Traditionally, the stability analysis is oriented to the influence of node dynamics, that is the models of and the parameters of generators and loads featured by the function Fi. The methods are mainly based on the sensitivity analysis and the Lyapunov or energy function. The former one is more numerical, while the latter one is more theoretical or analytical. Meanwhile, the power network structure and the network parameters are simply treated as some coefficients in the system model. So now let's see another related problem, namely network consensus that receives much attention from a control system community. I think Carol has also mentioned this typical model in his talk. And the dynamical model for network consensus takes the following form, which can be rewritten as the matrix form below, x dot equals to minus Lg times x, where Lg is the Laplacian matrix of the underlying network structure, and the x is the vector of node variables. A well-known result on network consensus says that a consensus is reached if and only if the Laplacian matrix is positive semi-definite with only one zero eigenvalue. Moreover, we observe many analogies between the network consensus and the power system dynamics. First, they both have network structure information embedded into their dynamics. Second, reaching a consensus is very similar to that all generators in a power system have synchronized rotor speeds, which indicates stability. So considering the fact that network consensus and power system dynamics share many common properties, and there is already graph-based theory for checking consensus. So we are motivated that there should be something similar, some similar type of theory for power system stability, which has been paid little attention. So that's why we conduct a network-based analysis for power systems. So we now come to the details of the network-based angle stability analysis. We adopt the so-called structure-preserving model for angle stability analysis. So borrowing the network science terminology, this model is actually a mix of second-order and first-order Kuromoto oscillators, which respectively describe the dynamics of generators and loads. And the structure-preserving model is a simplification of the real situations in power systems that captures the key feature of the rotor angle behaviors. Also note that this is a natural model to study the impact of power network structure, because the network information contained in this model directly correspond to the physical network. Then eliminating the differential terms in this model, we have the following equilibrium equation, which is usually called the active power flow equation in power system community. So with this model, we introduce the formal definition of rotor angle stability. It refers to the ability of synchronous generators in a power system to maintain synchronism under disturbances. In the context of the structure preserving model, rotor angle stability means the rotor speeds of all generators get synchronized here, and the rotor angles converge to the equilibrium manifold. So this term represents the equilibrium manifold. So any point in this manifold has the same physical meaning as the point theta e here. And traditionally, the local stability analysis is carried out by checking the eigenvalues of the system Jacobian around an equilibrium point. And in the following, we will carry out a new analysis from a network perspective. So for the sake of the stability description in terms of network structure, we define the power flow graph and the critical lines as follows. So the active power flow graph has the same topology as the underlying power network, with a set of nodes V and set of edges E, and the line weights are given by the following equation. And in the power flow graph, a line ij is called a critical line if the following inequality is satisfied. So we note that the active power flow graph is a signed graph, because the critical lines induce negative weighted edges in the graph, which will play an important role in the following analysis. We now introduce the concept of hyperbolicity, stability, and type of equilibria, and link angle stability to the Laplacian matrix of power flow graph. So let's use this notation, J dyn, to denote the system Jacobian at an equilibrium point. Then this equilibrium point is hyperbolic if the Jacobian matrix has no eigenvalues with 0 real parts, and a hyperbolic equilibrium point is locally asymptotically stable, and if it has no eigenvalues with positive real parts. Otherwise, it is a type M UEP, where n is the number of the eigenvalues with positive real parts. So the type of UEP refers to the number of unstable manifolds around an equilibrium point, which is an important geometric description for the stability region. So that's why we also take it into account. So then we have the following theorem saying that the equilibrium point is hyperbolic and locally asymptotically stable if and only if the corresponding Laplacian matrix if the Laplacian matrix of the corresponding power flow graph is positive semi-definite with only 1, 0 eigenvalue. Further, if the equilibrium point is hyperbolic and unstable, then the type is given by the number of negative eigenvalues of the Laplacian matrix. So this theorem is a fundamental result that links hyperbolicity, stability, and type of system equilibria to the spectrum of the power flow graph Laplacian. With this fundamental theorem, we further characterize a rotor angle stability by the effective resistance. So here we propose an extended definition of effective resistance as follows. So we will not explain the complex expression here, and instead we will get an intuitive understanding of this definition by circuit analysis, which will be shown in the next page. So also note that the effective resistance is a common concept in graph theory. I think Carrier has also just introduced the detailed definition of the effective resistance, but its traditional version only applies to a pair of nodes to describe the coupling between them. And this extended definition makes a generalization which can describe the coupling between any two sets of nodes, any two disjoint sets of nodes, to be precise. And this is more consistent with the nature of power systems, as well as other engineering problems over networks, because many dynamical behaviors observed in reality are concerned with the interaction between two groups of nodes rather than a pair of nodes. Moreover, we have proved that this extended definition preserves the monotonicity and the convexity held by the traditional version. So let's move on to this page that illustrates the circuit meaning of the extended effective resistance. So let's interpret a graph into a resistive network. That is, the network has the same topology as the graph, and the line conductance is given by the corresponding edge weight. So in such a resistive network, we suppose each node in the set A has current injections, and the total injection is 1, and each node in set B has current ejection, and the total current ejection is 1, and all the remaining nodes are open circuit. Then we have proved that the minimum energy dissipation under this setting is equal to the effective resistance between set A and B. In other words, the network can be equivalent as the circuit shown in the right. These two clusters, which represent the aggregation of node set A and B, are connected by a resistance, and this equivalent circuit has the same energy dissipation as the original circuit. And the extended effective resistance also has physical meanings in terms of potential difference and the current flow, which are omitted here due to the time limit. So let's go back to the rotor angle stability, and we have the following results linking stability to effective resistance and the critical lines. So, so the first theorem implies that the rotor angle instability is equivalent to the appearance of some negative effective resistance between certain two sets of nodes. And recall that in the network consensus, the negative weighted lines are referred to as antagonist interactions between the nodes. So borrowing this term, we can interpret the negative effective resistance in the power systems as the electrical antagonism. So the first theorem interprets the angle instability as the electrical antagonism between certain two sets of nodes induced by the critical lines. And the second theorem implies that the number of unstable manifolds around an unstable equilibrium point is upper bounded by the number of critical lines. It provides new ideas into linking the unstable manifolds, which is a mathematical concept, to physical components in power systems. So note that the effective resistance can only provide an upper bound for the type of UEP. So for a precise evaluation of the type of UEP, we need to resort a matrix condition shown in the following theorem, saying that the equilibrium point is hyperbolic and locally asymptotically stable if and only if the following matrix is positive semi-definite with only one zero eigenvalue. And this matrix M gives a more comprehensive description of angle stability and the type of UEP. Meanwhile, it inevitably takes a more complex form. So generally, the diagonal block here represents the impact of the locations and the weights of the critical lines, and the off-diagonal block here and here represents the impact of the possible cut sets formed by the critical lines, and you can refer to the reference below for more details. So now let's move on to some other results we recently developed. Apart from the transmission systems that we have discussed so far, microgrids are a class of emerging power systems which have a flexible architecture to enhance the reliability of power supply. So there is a common observation in microgrid stability relating to network topology, saying that the stability level declines with more distributed generators connected in a tree-like manner. For example, if we keep adding generators to the terminals of the four-node system shown in the left, then we end up with a system with long feeders as shown in the right figure. And meanwhile, the system stability continues declining, and finally, it loses stability here. So this type of phenomenon has been observed in many groups around the world, and it is usually assumed that such an instability event is caused by the bad tuning of the node parameters. However, we reveal that it is the network structure that is to blame for. We find that the algebraic connectivity of the Laplacian matrix of the underlying microgrid network plays a key role in this event. So here the algebraic connectivity refers to the second smallest eigenvalue of the Laplacian matrix. So as the following theorem implies, the tree-like connection between the nodes leads to zero algebraic connectivity, and further the zero algebraic connectivity leads to a zero eigenvalue of the system Jacobian matrix, which indicates instability. So therefore, we provide a graph theory explanation to this instability phenomenon, and such type of instability is purely by means of improper connection pattern, no matter how perfectly the node parameters are tuned. Moreover, we have also established a network-based result for power system voltage stability. So commonly, the limit point for voltage stability is indicated by the singularity of power flow Jacobian matrix, and we define the concept of network load admittance ratio as a specific eigenvalue of the matrix, which is a product of the power, which is a product of the power network admittance matrix and the inversion of load admittance matrix. Then the following theorem says that power flow Jacobian singularity is equivalent to the unity network load admittance ratio, and this result interprets the voltage stability limit as generalized admittance matching between the power network and loads. And again, you can refer to the following reference for more details. So now let's have a summary. In this talk, we have surveyed some network-based stability analysis developed recently. We have discussed the results on angle stability, microgrid stability, and voltage stability using different graph theory concepts and tools. So based on the network-based theory, we are now working towards the stability, the network-based control that regulates power system stability via tuning the network structure. So we hope that the network-based control will be a promising solution to the enhancement of power system stability in the future. So that's all for my talk. Thank you for your attention.
Thank you for that, Yu. So do we have any questions from the participants? Again, I see that there's no one who's left a question yet. You can leave questions in the question and answer session. Otherwise, I will just ask myself, is there anybody, are there power companies that are looking at this now, implementing these ideas? Is this something that's being looked at?
So I think, unfortunately, these results are still at the theory stage, I think. I think one reason for the power for our result not being so attractive to the current power companies is that because we are studying the role of different structure in the stability problems of power system, but the engineers in the power company are facing with the same network every day, so they are not so concerned with they are not so care about how the network structure influence power system stability, because the network structure they have will not change frequently. But I think in the future, this trend will be changed, because as I mentioned in the slides, there is an emerging class of power system called microgrids, which do have a very flexible and volatile network structure. And in these kind of power systems, which are becoming popular recently, I think the role of network structure will drawing more attention, not only from theoreticians, but also from practitioners.
Okay, thank you very much for that.